everybody, or good evening and good afternoon, depending on where you're at in the world. My name is Isaac Montoya, and I am the Director of Marketing here at Upsite Technologies. I would like to welcome and thank you all for joining us for our 4th annual Airflow Management Awareness Month. For those of you who may be unfamiliar, 4 years ago, we declared June as Airflow Management Awareness Month in the effort to not only raise awareness around airflow management, but also cooling optimization as a whole in data centers. One thing that we have come to find is, while airflow management and cooling optimization basics are maybe common knowledge, they're not necessarily common practice. So a goal of ours with a lot of what we do and with Airflow Management Awareness Month is to try to migrate the industry to not only common knowledge, but common practice and application. So today we're going to be joined by our Senior Engineer and Company Science Officer, Lars Strong. He'll be talking about a topic that has come up quite a bit in recent years, and he will discuss why for most data centers, liquid and air cooling will not be mutually exclusive. So before I pass it on to Lars, I want to just go over some quick housekeeping items. This is the first of 4 webinars as part of our Airflow Management Awareness Month webinar series. Next week, we'll be joined by Bill Clayman, the Executive Vice President of Digital Solutions for Switch, and he will be giving an encore presentation of his Data Center World keynote address. So if you missed it at Data Center World, you don't want to miss it next week. And after that, we'll be joined by Aaron Wemhoff, the Associate Professor of Mechanical Engineering and Director at Villanova University, as well as Rahan Khalid, a Graduate Research Assistant at Villanova University. And they will be presenting a recent project of theirs on thermal control strategies for energy efficient data centers. And last but not least, June 25th, the last webinar, we will be joined by Kevin Kent, the Data Center Operations Manager at The Ohio State University Wexner Medical Center. And he'll be talking about energy efficiency in data center and really beg the question of if your data center is up to the task of becoming energy efficient. So if you haven't already, please feel free to register for those upcoming webinars. Towards the end of this webinar, I will share a link with everybody for you to go ahead and register for those. So once again today, we are joined by Upsite Senior Engineer and Company Science Officer Lars Strong. Lars has been with Upsite since 2001, and before that, he was with the Uptime Institute. Lars is a certified energy data center energy practitioner, as well as an HVAC specialist. Lars is a recognized expert on data center optimization and a thought leader. Lars has spent over 20 years in the data center industry, with the majority of that being focused on cooling optimization. He has spoken at many conferences, both domestically here in the United States as well as internationally, on various topics regarding cooling optimization and data center operations. So we are glad to have him here, and without further ado, I will pass it along to Lars.
Thank you very much, Isaac. Well, welcome everyone. I really appreciate you taking the time to join us. And I'm looking forward to this presentation and sharing this information with you. You know, this is a expanding field of concern in data centers, and one of the main reasons that we put this presentation together is because of the conversations I've been having with customers, and I'll share more about those conversations with you as we progress. So I look forward to answering any questions that you have towards the end. We'll go through the presentation, and please, as things come up, if you have any disagreements or agreements or questions, please keep track of those and type those into the question and answer section. There's in the control panel for the webinar, you have a choice for typing in some questions. So we'll get to those at the end of it. So we'll get started with telling you a little bit about the presentation. I'm going to go through the timeline of adoption and walk through where liquid has been, how close it has been to the heat source, and how that process has evolved. I'll talk about some of the drivers for liquid cooling. Some of those are well known, some of them not so well known. And we'll talk about just the general consideration of hydrophobia, just the fear of water in the data center, and the proximity of liquid in the data center, and the proximity of liquid to the IT equipment. I've got a number of graphics that'll we'll walk through, and it'll put in perspective just the process that the industry has gone through and where we're at. We'll share some types of liquid cooling, and so you can get a sense of that. A few pictures to see, some physics of liquid cooling, which will be really important because there's a lot of hype in the industry. And I wanted to share some of the physics of what's going on. And then we've got a case study for you that's going to really put the topic of this presentation in perspective. That for most facilities, liquid and air cooling are not going to be mutually exclusive. They're going to be coexisting for the foreseeable future. And in that, we need to know how to do both well. So that's what we'll go through. I look forward to the discussion questions with you at the end. And to get started, I want to tell you a little bit about our history. Many of you know of the name Ken Brill. I started working with Ken well over 20 years ago, and when we were working at the Uptime Institute. And with Ken, we did some research, and we quantified the amount of bypass airflow occurring in the room and how poorly people were sealing openings in the raised floor. And Ken saw that problem and really wanted to help everyone. So we developed the first brush grommet in the industry and coined the term bypass airflow. So through that process, Upsite Technologies was born to be a separate company to provide airflow management solutions and consulting services to the data center industry. So Ken has really done a lot for the industry, and he's known as the father of the data center industry. And all of the products and services that we deliver are founded in rest on that foundation of research and best practices. So let's get started here with the adoption of liquid cooling and walk through this timeline. I want to just first say that it's really important to know that liquid has been in the data center for a long time. And through this timeline, I'm going to walk through and share with you where it was, where the liquid went, and where it is now. And I want to make it also really clear that I'm not here to sell you on any particular solution. I'm here to provide an education and perspective for what's happening in the data center industry. And we see here on the timeline that we start in the early 1970s through mid-1990s with mainframes. And there are still some large mainframe supercomputers that are water cooled, but it was way back in the early 70s that mainframes had liquid coming into the computer room, running up through the chassis and being liquid cooled. But even before that, liquid cooling goes way back. The first dielectric fluid used to cool transformers, that patent was filed in 1887. And even when it comes to computers, dielectric fluid was used for cooling a computer. The first patent for dielectric cooling of a computer was filed in 1966. None of these things way back then were not widely adopted at all, but it is not a new technology. It has been around for quite a long time. What's changing in the industry now is the adoption, and that it's becoming more and more prevalent. That process started to occur with gaming in the 1990s, that is, through 2000, gaming and custom-built PCs. A lot of power consumption was being packed into these small boxes, and they turned to liquid cooling for a means of getting that heat out of the box. And a lot of the liquid cooling vendors providing solutions to the market today got their start with solutions for the gaming community. I have next on the line here that in 2005 to 2010, about then is when chilled doors first entered the market. Now, a chilled door is not technically liquid cooling. There is liquid, of course, flowing through it, but I'll get into the definition of why that's not actually liquid cooling, but it's often included in the conversation, so I've included in the timeline here. Then, 2010 to 2015, HPC really started to have an effect on the industry and drive liquid cooling in the data center. And then later on, 2015 to present, direct contact and full immersion started to become used in data centers to remove heat. So that's kind of the process that we went through. And now I'd like to ask you a few questions, get a sense of who's joining us today. So you'll see a poll show up here. And if you could just take a moment and answer these questions of how large is your computer room and what's most important to you and in your company. Got a couple of options for you there. It might be something else, but whichever one is closest for you. You can take a moment and select that. So we'll share these results with you here in just a moment as we get a few more people to respond. So one of the things that I'm seeing as people are responding is something that points to what happens in the industry is, and I think it applies to liquid cooling very clearly, is that we hear all this hype about what's happening. We hear about PUEs of 1.1, and we hear about liquid cooling being adopted in these mega data centers, and they're pretty few. As we see here, most of our participants here on the call, most of the people that have responded, that is, have a smaller facility, the 0 to 5,000 square feet, a few up in the larger 10 to 20,000, and nobody has said greater than 50,000. So it's important to recognize that it's a different world for those of us with those operators with a smaller footprint than the ones that have very large and very deep pockets. So it's good to have you on the call with us. And the most important issue for all of you, obviously, as you can see, is reducing operating costs. And so that points to the efficiency, increasing IT equipment reliability second, and increasing cooling capacity is the trailer. And that's not surprising. There's generally way more cooling capacity in a data center than is needed. The question is that equipment being used effectively? All right, I want to plant a seed here and get you thinking a little bit. We have some information about a purpose-built liquid-cooled data center. Sandia National Laboratory is in the final stages of completing the construction of a new data center built specifically to house liquid-cooled equipment. And it's a 14,000 square foot facility, not very large, but dissipating at full load 10 megawatts of power. And they set out to have this facility be as focused on liquid cooling as possible. So I want to ask you put up another poll here and ask you, what do you think is the relationship, the percentage of liquid cooling to air cooling? So how far were they able to push it? Were they able to build a facility that was 100% liquid cooled and no air, or some other ratio? Take a guess and I'll share the answer at the end of the presentation. We'll give you just a few more moments for you guys to take a guess about that? Nobody's taking the bait. Oh, there, we got one person. Feels like maybe 100% liquid cooled was possible. And look, nice spread, wide range. And that's, I like seeing that because there are a lot of different ways that this could go. So I'll give you just a moment if anybody else hasn't clicked in, taken a guess. And again, we'll share the results with you at the end of the presentation. All right, thank you. Okay, let's get into this and talk about the drivers for liquid cooling. Of course, density is a major driver. HPC, high performance computing, is driving the liquid cooling industry. I was at a recent HPC event, and there were many different cooling vendors touting their solutions. And that's driven largely by latency. They want to keep the communication delay as short as possible. So they're packing all the equipment into small spaces, a single cabinet or cabinets adjacent to each other. Very high density becomes hard to cool with air. That's one of the misconceptions that I'll address a little bit later. Performance is, of course, another driver. Higher clock speeds require colder chips, and research modeling. The oil and gas industry with their enormous three-dimensional modeling and sometimes financial modeling requires just extreme compute performance, and that's driving some of the liquid cooling as well. And then economy. As most of you said, what's most important to you is reducing operating cost. And there are very substantial benefits that can be realized by going to liquid cooling for the efficiency. One of them is relating to the fans and the IT equipment. Approximately 20% of the load that goes through all the critical power distribution system, the UPS, the PDUs, and into the server chassis, 20% of that power gets consumed by the fans in the servers. So that is a significant load that can go away or largely go away with the adoption of liquid cooling. There are other aspects of liquid cooling that drive efficiency, such as using warmer chilled water, which can improve the efficiency of the chiller or provide other options for using waste heat from other processes, such as in warm water cooling. That can substantially reduce the CapEx and OpEx of the facility. So, I mean, a whole presentation could be devoted just to each of the bullets on this slide, but we're going to touch on the high-level issues in this presentation. And then one of the side benefits to liquid cooling is a more accurate PUE. As I mentioned that, 20% of the IT load is actually fans, which should be considered part of the cooling load and not actually part of the IT compute load. So by removing the fans, the PUE equation becomes cleaner and more accurate. You're getting the IT compute load on one side of the equation, and you're getting the infrastructure load on the other side of the equation. Let's talk a little bit about the hydrophobia. This was a term that was coined by Julius Nierdorfer, and it describes very well as, everybody wants to name things in the data center industry, and so we have a term here of data center hydrophobia, which is just the fear of water and the fear of having water in your space. And there's a few things that are driving that. Air is understood, in quotes. It's familiar. And I say understood in quotes because while it's familiar, it's not always done very well. There's substantial room for improvement in a lot of data centers. One of the challenges with air is that it's invisible. You can't see it. So it's hard to know how many CFM are passing through IT equipment and how many CFM are bypassing the IT equipment. So there's a lot of opportunity left in airflow management for improvement and making that process more efficient and lowering cost. But it is familiar, and the data center industry is very risk averse. So they're not ones to necessarily jump on early adoption. Then there's the care and handling paradigm concern, and the immersion cooling is probably the biggest one there. Putting all the equipment in a vat of liquid and the issues that come around with having to maintain that equipment is daunting for a number of people. Another one is the need to ask IT people to become plumbers. It's just not exactly something you want to be doing, asking IT people to be plumbers. But that, to some degree, needs to happen, or at least the awareness of the plumbing that's solutions that are occurring. White space, using up more space is a concern, particularly with immersion. There's the risk of liquid in the cabinet. People are concerned about electrocution and outages, having water or liquid close to electricity. But these are things that can be mitigated with best practices. And it's not that this is something new. This has been done for a long time, as we'll talk more about. There's also no standards right now. There's a lot of different solutions in the market. People are bringing a lot of different things to the market, and they're changing very rapidly. A lot of different vendors saying this is touting the best solution. So people don't really know where to go, and that's one of the reasons that I'm doing this presentation, is to help clarify the considerations. There's, of course, the capital cost concern of people implementing another cooling system, and depending upon the facility that you have, you may or may not need to add additional infrastructure. But regardless of whether you add more infrastructure or not, there will be the additional capital cost of running, the additional complexity, that is, of running two systems. Now let's talk about the definition of liquid cooling. I mean, this is really important in being able to have informed conversations about liquid cooling. Kinbrill had a saying which was power in, heat out, always. Every kilowatt of electricity that goes into a data center building becomes a kilowatt of heat that needs to be removed from the building. This includes all the IT equipment, of course, all the fan motors, pumps, transformer losses, distribution losses, all of those things consume kilowatts of electricity and turn it into kilowatts of heat that need to be removed in some way. So liquid cooling is when the removal of the heat is done by liquid. When the first loop that carries away the heat from the heat source is liquid, that's liquid cooling. And I'll talk about these concepts of loops of heat removal here in a moment. Many of them are required to cool and remove the heat from the building. Let's show you a number of pictures here. So these programs talk about heat exchangers and ultimately immersion, and you'll see that the names and these dots here will change and indicate in orange where we are in this progression in this timeline. But for all cases, we've got electricity coming into the computer room, and that electricity is being consumed by some device. And as I said, every kilowatt of electricity becomes a kilowatt of heat that needs to be removed. So starting here in the mainframe days, we've got a big box sitting in the computer room on the slab or the raised floor, and we've got chilled water. We've got water flowing through the chassis, picking up that heat, taking the heat out of the chassis with liquid, and likely taking it to a chiller, and then with a heat transfer, the process that occurs in the chiller, that heat is transferred to another liquid, to the condenser water, and that condenser water carries the heat out to a cooling tower of some form where the environment can pass through and the heat is ultimately rejected to the atmosphere. So in this case, we had these two loops of liquid and then the final loop of air to remove the heat from the room. And so liquid was very close. It was up against the source of the heat in the computer room. So now moving to the server phase of the industry, when IT equipment started to be designed to fit in these discrete U units, the decision was made to switch to air cooling because it's such a flexible solution. All the equipment is immersed essentially in air. You put a fan in it and it's going to suck air in the front and blow air out the back, and it's going to take care of itself and cool itself. Hopefully you're providing the right inlet air temperature to the face of the cabinets, but it's essentially going to take care of itself quite flexibly. This is when we have air cooling. We have air as the first loop. Air is what's picking up the heat from the source and carrying that heat to a perimeter cooling unit, be it a cray in this case with a chilled water loop, or it could be a crack air conditioner system with a refrigerant cycle. But we have the perimeter cooling units picking up the heat from the air, and now the heat enters a liquid, and the liquid is going to carry the heat away, either directly outdoors if you have a compressor-based system, or to the chiller again if you have a chilled water system, passing it to the condenser water and out to the cooling tower again. So moving on to the in-row cooling, we now, instead of having the cooling at the perimeter of the room, we move the cooling closer to the load. Now we have cooling units. Basically, it's a small cooling unit sitting in the row of the cabinets. And we're just showing one loop of air here, but of course, the air that's coming out of this cooling unit is going and serving all the IT equipment in this row. And it's the air that's the loop that picks up the heat, brings the heat back to a cooling unit where a heat exchange process occurs to pass the heat to the liquid. And then the liquid carries it out of the building once again. So we've moved the heat, we've moved the liquid a little closer to the heat source in this case. And now moving to the next step, to rear door heat exchangers, we're getting now the liquid on the back of each of the cabinets. We have a rear door heat exchanger mounted on the backs of each of the cabinets. And rear door heat exchangers are often referred to as a liquid cooled solution. They do have liquid flowing through them. And so there is liquid cooling occurring in that sense, but it is not truly liquid cooling because liquid is not removing the heat from the source. Air is still removing the heat from the source, and it's only carrying it for a couple of inches before it passes that heat to the liquid flowing through the radiators in the rear door. And then again, through the loops of liquid to pass the heat out to the environment once again. Here is the first time that we get liquid back to the source. So with touch cooling, we have now either a row-based cooling distribution unit is shown in this picture, or they could be rack-mounted cooling distribution units. But this is, again, another liquid-to-liquid heat exchanger that transfers the heat that is picked up from the IT components by liquid to a liquid that is used to carry it out of the building. So we have liquid now for the first time flowing through each of the components, could be in each of these cabinets, picking up the heat from the heat source and bringing that heat back, transferring it to another liquid. We also have the loop of air passing through the cabinets. Now there's two reasons that this could be happening. We have potentially IT equipment that is not liquid cooled, that requires air cooling, or the liquid cooled device is not 100% liquid cooled. There's still a fan running. Maybe it's only running at 20% of the speed that it would have run if it were purely air cooled, but there still might be a fan with some flow of air required to keep some of the components cool that liquid cannot pick up the heat from. So we have a true hybrid situation here where we have the two loops, one air and one liquid picking up the heat from the source. This diagram, of course, represents immersion cooling, which simplifies things in a number of ways. We now, there's no air cooling possible here. Everything is immersed in a tank, and 100% of the heat that is produced by the components that are in the tank is picked up by a liquid. And there's a number of different liquids that are used. I'll talk about that a little bit more in a moment. But these liquids pick up the heat from all the components that are in that tank, and then with another heat exchanger, pass that heat to another liquid that then is taking it out of the building. There might be a chiller involved. In most cases, there isn't. Depends on how the system is set up, but heat leaves the room through liquid and then ultimately rejected to the atmosphere as before. Here's some photographs of the types of liquid cooling that we've been discussing. So here's a rear door heat exchanger. This is an active version where there are fans mounted that help draw the air through the cabinet, in addition to the fans in the IT equipment that are moving air through the IT equipment. And then the radiator picks up the heat. So this is, now that we've discussed the definition of liquid cooling, which is liquid picking up the heat, this is not liquid cooling, it's close coupled air cooling. And there's a couple of other devices that enter into that same category, which are in-row cooling and over-row cooling. There are cooling units that are mounted to the ceilings or along the tops of the cabinets, and in-row cooling units, of course, either passive or active, or all forms of close coupled air cooling. Here's some images showing different types of direct contact liquid cooling. So there's a number of manufacturers out there that are providing these solutions. And for each of these, we have an inlet and an outlet tube, and we're bringing liquid in across the chip and other components that are producing heat, and then out again. Some of these are passive in that there's no pumps inside the trays of equipment, and some of them have a pump in a number of locations to help move the fluid through the different components. So there's a number of different ways to approach this. Rigid connections, flexible connections. The amount of heat that is picked up varies by the different providers, and the liquid that is used varies by the different providers. But these are all forms of direct contact liquid cooling. Another form of touch cooling that is not quite as well known is fixed cold plate cooling. And this is a solution that was developed by our parent company, Aquila. And this solution involves manifolds that are at the back of the cabinet, and they are permanently affixed to cold plates that have the liquid flowing through them. So there's no connectors in this solution. This is all manufactured ahead of time and pressure tested, and there's no need to ever disconnect or reconnect any of these fittings. It's all a permanent fixed solution. The uniqueness of this is that these trays that hold the IT components can be lowered and then removed from the cabinet and put back in and pressed up against the cold plate without doing any plumbing. So there's no need to ask IT people to become plumbers in this solution. They can focus on their job of doing their IT work, and the liquid is just there to remove the heat. The way that it works is each of the power producing components has a aluminum heat spreader that sits on top of it, and the heat conducts through that heat spreader and then through a thermal interface material up against a cold plate with the warm water flowing through it. and that removes the heat. Warm water can be used, quite warm water, up to like around 115 degrees Fahrenheit, 46 degrees Celsius water can be used and still keep the processors at an appropriate operating temperature. So this opens up the possibility of using waste heat. Now, like the other touch cooling, there's a cooling distribution unit down at the bottom of the cabinet or in the row, a row mounted cooling distribution unit, which is another liquid to liquid heat exchanger for passing the heat to the facility liquid that will remove the heat from the building. Here's some images of the immersion cooling. There's a number of different providers out there using a number of different fluids, such as Novec or Fluorinet and Flow Inert. And obviously, we have tanks now, basically a cabinet on its side, and all the equipment sits in the vat of liquid. There's single phase and two phase. Two phase means that the liquid boils off, becomes a gas, and then condenses again back to a liquid. And there's single phase, which it just stays a liquid the entire time. In this two-phase solution, normally this lid would be closed and this gas would just be condensing on the coils and dripping back into the tank. There's some benefits to this. Every component that is sitting in the tank, 100% of the heat is picked up by the liquid, but it uses up more floor space. It's messy in some cases. A lot of people having experience with this, experience the mess being a particularly challenge. And the liquid, if it's the more viscous oil-based solutions, require a significant amount of energy to distribute that liquid around through the tank. You need to keep that liquid moving or components will overheat. So I'd like to talk now a little bit about another really important reason why liquid and air are not mutually exclusive, and that there's going to be, they're going to coexist. There's two reasons. One is that not all equipment can be liquid cooled, and then so there's going to be some equipment that is outside of a liquid cooling solution that's not going to be an immersion, or it's not going to have direct contact liquid cooling, so it's just not included in the liquid cooling solution. And then there's equipment that, even though it can be liquid cooled, not all of the heat is picked up by the liquid. Some of the heat is picked up by the air. So just looking at the cabinet level in this slide, this is for a cabinet that is liquid cooled, how much of the heat is picked up by liquid and how much is left to be picked up by air. So we have the different types of cooling. Immersion cooling picks up all of the heat of the equipment that is in the tank, leaving nothing needed to be picked up by air. The two forms of touch cooling, direct contact liquid cooling, somewhere around 65 to 75%, and these numbers are increasing as these solutions are refined. Somewhere around 65 to 75% of the heat is picked up by the liquid, leaving 25 to 35% of the heat to be captured by air. The fixed cold plate solution picks up 93% of the heat, approximately, and this is the result of an independent study done by NREL, leaving 7% of the heat to be picked up, to be dissipated in another means. This is such a small percentage that in a fixed cold plate solution, no fans are necessary. So the liquid is picking up the bulk of the heat, and the rest of the heat just kind of convectively or conducts out through the cabinet and is picked up by the ambient air. So no fans are required for this solution. In many of the direct contact liquid cooling solutions, fans are required, but they're running at a very low speed, so they've really benefited from the fan affinity law, and they're using a very small fraction of the energy that was used when they were, a full air-cooled solution. So with the close coupled air cooling, rear door heat exchangers, and in-row cooling, none of the heat is picked up by liquid, not from the source. So those are not actually liquid cooled solutions. 100% of the heat is being picked up by air, and then it's giving that heat to the liquid. Then if we look at the room level, we talk about, well, okay, so what components, what types of equipment can, is a good fit for liquid cooling, and which is going to remain sitting in the room requiring air cooling. We look at, compute processing, chips, and switching and solid state storage, spinning media, power supplies. All of these things air can do quite well because air is so flexible. It can go in and around just about everything without causing any problems. So we won't talk about that. But for touch cooling, the processing can be easily done by both touch cooling and immersion. Switching with lots of cords and ports, that becomes a bit difficult. It's in development, but it is a challenge for both touch and immersion cooling. Solid state storage can be cooled by both solutions. Spinning media is something that can be done by touch cooling. For immersion, that spinning media needs to be sealed. It needs to be a helium disk drive, a sealed drive, so that no liquid can get in through the vents that are in some of the hard drives. Power supplies, again, air can handle that, of course, and it's in development for touch, and it's something that immersion cooling can handle. So this is why you're going to have still some air and some liquid cooling regardless. Not everything is a fit for liquid cooled solutions, at least not yet. Now I've got a bunch of numbers on the next few pages for you. This is the physics of liquid cooling, and I want to share this information with you because it helps dispel the hype that is existing in the data center industry. I've heard numbers being thrown around of 2,000 times better or 3,000 times better, that liquid cooling is the only answer going forward. We've reached the limit of what air cooling can do, and now we've got to turn to liquid. Well, that's not entirely true. I mean, it's absolutely true that liquid is a better medium for carrying away heat than air, but it's not as good, and air is not as bad as a lot of the hype. One of the numbers that I hear often thrown around is that air can only handle up to 20 kilowatts in a cabinet. And I know of a number of facilities that are doing 40 plus kilowatts in a cabinet with air. There's some extreme setup that's required for that, but it is possible to cool a lot more than 20 kilowatts in a cabinet with air. It does present challenges. So liquid definitely has its advantages. And let's look at some of the comparisons of these different properties and conditions and how they apply to the two different solutions. So one is the space available for the fluid, whether it's air or liquid, to be flowing through. When we have liquid, we have either a 1/4 or an 1/8 inch pipe for many cases, and these have very small flow areas, whereas air is likely to have several square inches. If it, 3 square inches is available, that's 60 times more area available than a 1/4 inch tube. The density of air shows that the density compared to the density of water, that water has a density that's 842 times better than air. The specific heat of air and compared to the specific heat of water, shows that water is only 4 times better than air, given the specific heat alone. Looking at the convection heat transfer equation, we have the amount of heat transferred is a function of the transfer coefficient, the area that the transfer is occurring over, and the temperature difference between the two surfaces, between the surface that is giving off the heat and the temperature of the fluid flowing over the surface. So if you change the area, you have a big effect on how much heat can be removed. So looking at the coefficient for air versus the coefficient for water, water ends up being 30 times better than air. Looking at the surface area available, water flowing over a chip might only have 1 square inch of surface area, whereas air flowing over a heat sink, aluminum finned heat sink or a copper finned heat sink, might have 10 times the surface area. So just looking at the coefficient of heat transfer and the surface area, putting those two numbers together, we end up that water is just 3 times better than air. So none of these is the exact case for what liquid cooling is compared to air. Each of these variables changes given the particular solution that is being used. I share this information with you so that you can have informed conversations about the process and evaluate solutions with more understanding and hold the vendors accountable for their hype. So let's talk a little bit about the key takeaways, and we're getting close to the conclusion of the presentation here. So if you have any questions, please get ready to share those. So obviously the definition of liquid cooling is really important, that liquid cooling is when liquid is what removes the heat from the source, from the chip, from the memory, from the GPUs, from the CPUs. Also, depending on the component and the solution, only a portion of that heat can be removed by the liquid. So not all of the components in a tray of equipment in a U space is removed by liquid, leaving some required to be cooled by air. And you can't put all IT equipment in liquid in immersion, and not all IT equipment is compatible with liquid cooled solutions. So you're going to have some equipment that still requires air cooling. And it's of course not the question, which is better. There's advantages to each. Air, you cannot argue with the flexibility of that solution. Liquid, you can't argue with the ability of it to carry more heat than air. What's the right choice for your facility depends on a number of factors. And want to make sure that you take away the realization that liquid is in the data center is not new. The question has just been, how close has liquid been to the heat source? And that a while back, it was very close, it moved away, and now liquid is getting closer and closer to the heat source again. So this last bullet, that liquid and air cooling will not be mutually exclusive. Hopefully that's been pretty obvious to you as we've gone through this presentation. But I'd like to share now with you the results of that question that we asked you before about the case study. So Sandia National Laboratory set out to build a purpose-built liquid-cooled data center. And their goal was, their design considerations were 14,000 square feet and 10 megawatts of heat dissipation. And here's what people guessed. We had a couple people guessing they were able to pull off 100% liquid cooling. Most people, 85% liquid to 15% air. and then tapering out with lesser and lesser amounts of liquid. So a number of you might have read a white paper. You guessed quite well. The results are that they came to the conclusion that they would need to account for, that they would be able to use liquid for 85% of the cooling, and that they would need to augment that with 15% or 1.5 megawatts of air cooling. So they have a few perimeter cooling units around the room to pick up that heat that is either given off by components that just can't be put in liquid, don't have a liquid cooled solution, or that the liquid for the solution doesn't pick up. So well done. Glad you participated in that, and a lot of you got that right. All right, well, here is my contact information and a list of the ways that we communicate. I encourage you to, if you don't already, to follow our blog series. We blog weekly, and that information is highly educational. We do very, very little selling in those articles. It's industry experts talking about issues in the data center. So with that, let's open it up to questions. I see we've got a number of questions that have come in, and we'll take a little time to try and answer those for you.
All right, great job, Lars. So we'll go ahead and jump into the questions that have been asked already. The first one for you, Lars, is what is the growth rate of the data center liquid cooling market?
Well, there's a number of people that are making predictions about that. And the numbers that I've heard are 15 to 30% compound annual growth rate between 2018 or 2019 now up to 2025. So somewhere between 15 to 30% is what people are predicting as the growth rate. And that's based off of approximately a $800 million industry right now, growing to 2.5 billion in 2025 is some of the rough numbers that I've been seeing of people of predictions.
Okay, so the next one is, how close in efficiency can we get to liquid cooling with an airflow optimized data center?
That's a good question, and I don't know that I can give you a number. There's so many variables involved, and one of them is the relates to the tier level of the infrastructure. So if it is, say, a tier 4, take the extreme example, a tier 4 fault tolerant infrastructure with dual concurrently maintainable electrical and mechanical distributions, then it's going to be inherently less efficient. And if then there's the environmental factor. If the facility is sitting in, the northern US, or if it's in, down in Arizona, is going to have a huge effect. So I can't give you a specific answer, but a liquid cooled facility is more efficient than even an air flowed, an air optimized cooled data center. But there is usually significant room for improvement with air-cooled facilities. We're seeing PUE numbers of air-cooled facilities, in the 1.1s, or the 1.2s, 1.3s, 1.2s, not uncommon. So that's a very efficient facility, and a number of things have to be done to achieve that. So that's about as much as I think I can give you. I'd be happy to discuss this offline and get into more detail with you if you'd like.
Okay, the next one is, do I have to have a chilled water system to add liquid cooling?
Good question. No, you do not have to have a chilled water system. That does make it easier to just tap into the chilled water and use the chilled water for the liquid cooling, but it is not necessary. And even though a facility has chilled water, it doesn't mean that that's always the right solution. Sometimes it might be a more appropriate solution to set up a separate liquid supply and dissipation to the environment, because you can operate the liquid cooled solution at a higher temperature than the chilled water might be for facilities, especially if that facility has mixed use and has office space as well.
Okay, the next one we got is there a rule of thumb or recommendation as to when to use these solutions in row, heat exchange door, touch, etc., regarding the kW per rack? Example, and do not consider the examples as accurate, crack or cray units, less than 10 kilowatts per rack, in row solution, 10 to 15 kilowatt per rack.
So I would say, I appreciate the question. I think it's clear to me. I'd say that the consideration of whether to use rear door heat exchangers is not so much what the cabinet density is, it's whether the configuration of the room and the existing cooling units can handle the load, whatever that load happens to be. Rear door heat exchangers are very often a reactive solution, meaning they are implemented after problems are occurring, and there's nothing wrong with that. Point is, IT equipment gets added in a room, and for whatever reason, there's two primary reasons. One, there's a lack of airflow management, and the other is there's a lack of cooling capacity. For one of those two reasons, the added IT equipment is causing hotspots, causing problems in the computer room, and so more capacity is needed. And so rear door heat exchangers are added to those cabinets to absorb that heat and remove it from the room and take the burden off of the perimeter cooling units. In many cases, I sound a little bit like I'm, stuck on this point, but airflow management can be improved if doors have not been implemented and containment of the aisles and really thorough containment of the cabinets, such as blanking panels, haven't been done. They can have a very adverse effect on the ability to cool the equipment and keep the room efficient. So in time, study after study, I see CFD analysis and being on site, making measurements, the importance of simple things like blanking panels and sealing under the cabinets and doors on the ends of the rows cannot be underestimated. It has a huge effect on the ability to take care of the equipment. So I've talked all the way around your question and not given you a kilowatt answer, but that's because I don't think I can give you one. But again, happy to get into the specifics of your facility and your question offline.
Okay, so we got a couple minutes left here, so we'll probably get to two more questions. The next one is, so there will never be a data center that can be fully liquid cooled, even with Immersion technology?
Would you repeat that question one more time, please?
So there will never be a data center that can be fully liquid cooled, even with Immersion technology? Sounds like.
Yeah, so it may be a higher percentage than, say, what Sandia Labs was able to create. Maybe it ends up being 90-10, 90% immersion cooled and 10%, or maybe even 95. Those numbers could increase over time as we see both the technology of immersion cooling and the choices for components going into it being designed around that solution, those numbers could go up. But yeah, there will always be a small percentage, or maybe a larger percentage. We'll see how that evolves. Yeah.
Okay, and this is going to be the last question before we jump off. In touch cooling or warm water cooling with cold plate, is there a possibility of accumulation of heat which will not be transferred and there is not much movement of air below the plate?
Yeah, so there will be there's not much movement of air, correct? And there will be some heat trapped in some spaces. But in an actual installation and a rigorous test scenario, that did not become a problem. Those pockets of heat were able to be maintained at an acceptable level as they eventually did convectively or through conduction get into the cold plate somehow or get out of the cabinet. So it didn't create a problem.
Okay, well, I think that's all the time we have left for questions. If we didn't get to your question, we'll answer those offline. Again, thank you all for joining us here for our 4th annual Airflow Management Awareness Month. Please make sure to register for our upcoming webinars in the coming weeks. And thank you all again, and thank you, Lars, for a great presentation.
Thank you, everyone, for your time.